Hello everybody. So today I will talk about the operational amplifier. So the operational amplifier is this triangle here. It has two inputs and it has one output. I call it the magic triangle. Why? Because it is a very simple device but can do a lot of applications. It can do most of the mathematical operations. Like for example, you can add, you can subtract, you can integrate, and you can differentiate. Besides, you can do also some amplification. Amplification means that if you have, for example, a small signal, a weak signal, and you want to amplify it. Amplify it means that you increase the amplitude, like, for example, the sound amplifier. Or you can do the opposite. If you have any source of noise and you want to decrease it, so also you can do that using the operational amplifier. So this is how it look like in theory. We draw it like this. So you don't care too much about this negative and positive. So you have these two inputs and one output. In reality, it is a chip like this. It's called it IC, integrated circuit. And this chip had 1, 2, 3, 4, 5, 6, 7, 8 legs. So if we want to look at inside this chip, here it is how it look like. And this is a notch here. This notch shows you how you number the legs. So this leg is number 1, 2, 3, 4, 5, 6, 7, 8. And from inside, leg number 2 and 3 are for the inputs. So this is the same like this 2 here. So this is leg number 2, this is leg number 3. For the output is leg number 6. Okay, so these are the three legs that we are using, number 2 and 3 for the inputs and number 6 for the output. Okay, this is a device that we call it active device. Active device means that you have to connect it to DC source to work. Exactly like, for example, if you have in your cell phone, if it is not connected to power, it will not work. Your laptop, if it is not connected to power, it will not work. If you don't have a battery, if you're not connected to power, it will not work. The same like this one here. If it is not connected to power, will not work. So how to make it work? That you connect leg number 7, you see, this leg number 7, to positive voltage, and the leg number 4, this green one, to negative voltage. And this positive and negative voltage depends on the what kind of chip you are using. Each chip has a data. There is a data sheet for it, and it tells you exactly what is the minimum voltage that you have to use to make this operational amplifier operate. For example, sometimes it is positive 10 and negative 10, positive 15 and negative 15, positive 18 and negative 18 volt. More usually, it is the voltage is positive and the negative is the same value. So to positive 10, for example, it is negative 10 also. The ones that you have in the lab, I selected the chip that can operate with positive and negative 5 volt. Why? Because this is what's available. The analog discovery board, it can give you positive and negative 5 volt. So that's why I selected the chip in lab number 9. That you will see it in lab number 9. Okay, but when you have problems, usually we do not draw this red and this green. We just draw this part here. Okay, so we assume that it is already connected to positive and negative DC voltage. What we need to remember here is that if you have AC signal, for example, and the amplitude is 1 volt, okay, and you want to amplify to make it, for example, 100 volt. 100 volt. So you need to multiply by 100. Okay. If the DC voltage is 10, for example, or 12, let's say 12, positive 12 and negative 12, you cannot exceed this number. You cannot get an output that is more than 12, for example, the DC voltage. Okay, this is exactly like if I give you $100 and I ask you to go to a Walmart, for example, you cannot spend more than the $100. This is exactly the same. So here, what you give to the operation amplifier is the maximum that you can get from the operation amplifier. So if you run the operation amplifier by a DC voltage that's, for example, 12 volt and negative 12 volt, you cannot get the output more than this 12 volt. This is the maximum that you can get. Okay. So now let us see how this operation amplifier operate. So this is in general, this is how it look like from inside the operation amplifier. It has an input impedance or input resistance and output resistance. Ideally, this input resistance is 0 and the input resistance is infinity. But of course, this is not the case. But when we solve the problems in this chapter, we assume that the input resistance is infinity and the output is 0. So in this case, if the resistance here is infinity, you do not have any current here. You will not have any current input to the operation amplifier. Okay, that's why to solve any operation amplifier problem, you always assume that this current is 0 ampere, and this current is 0 ampere. So this will be number 1. To solve any problem in operation amplifier, you assume that the current is 0. Second thing is these 2 voltages here are the same. They are the same voltage. So V1 here is the same like V2. So this is all what you need to remember to solve any problem in operation amplifier, that V1 and V2 are the same and the input current is 0. And once you do that, you forget about the operation amplifier and you solve the problem as you solve any problem, regular problem. So again, this is the ideal operation amplifier. All what you need to remember is that the current is 0. This I equals 0. I1 and I2 are 0, and V1 and V2 are the same. They are the same voltage. That's it. Very simple. Okay. So these are the steps to solve any operation amplifier problem. Number 1, the input currents is I1 and I2 are 0. Number 2, V1 and V2 are the same. Okay. Number 3, apply nodal analysis at the input of the operation amplifier. Apply nodal analysis at the input of the operation amplifier. Okay. Never, remember this, never apply nodal analysis at the output of the operation amplifier. Never apply it at the output. So don't apply nodal analysis at the output at all. Okay, don't do that. Apply it only at the input. You can apply it at this node or at this node, depending on the circuit. So let us take some examples. If you look at the circuit here, this one here, assume that this one here, assume that this one is connected to the ground. V2 is connected to the ground. So this means that V1 equal V2 will be 0. I1 and I2 are 0. That's it. So for this one, I1 and I2 are 0. Since V2 is connected to the ground, then V1 also is connected to the ground, will be 0. Second one here, again, I1 and I2 are 0, and V1 equal V2. V1 is connected to 9 volt, so V1 equal 9. The same here, V2 will be 9 volt. If you look at this example here, I1 equals 0 and I2 equals 0. V1 and V2 are the same. V1 is negative 9 because this is a negative. V1 is negative 9, then V2 is negative 9 also. If you look at this example, this current equals 0. Let us draw this. This current equals 0 ampere, and this current also is 0 ampere. This one is 0 and this one is 0. V1 equal V2. V2 equal 12, so V1 equal 12. So these two are the same. Okay. V2 equal 12 volt, then V1 also equal 12. So you have to write 12 here. So V1 equal 12 Okay, and then you apply nodal analysis at the input. You don't apply it here, of course. You apply it in at V1. At V1. When you apply it at V1, you have three currents. You have this current here in this resistor, and you have this current in this resistor, which is this one here. Okay, so and the third current is this one, which is already zero. We know this one is zero. Okay, so apply nodal analysis here, since it's V1 minus 0, this is a ground, V1 minus 0 over 3, there it is. And we know that V1 is 12. And then the second one here, this current, which is this one here, it is this voltage, which is V1, minus this voltage, which is VO. This one is VO, and this one is V1. So it is V1 minus VO over 2. V1 minus VO over 2. Okay? And so this is very simple equation. One equation, one unknown, because V1 is already 12. Then you can solve it and find VO. You can solve it and find VO. Okay? So let's look at the second one, second example, this one here. So again, you apply the three steps. Step number 1, current is 0, 0 ampere, and this one is also 0. Okay. Second, V1 equal V2. If V1 equal V2, V2 is 0, so V1 will be 0 also. So this one is 0 volts. This one is 0. Okay, 0 volts. Third, apply nodal analysis at the input. So we have these three currents, 1, 2, which is this current. Okay, and the third one is this one here, which is 0. So at this node, you have three currents. One is V1 minus, the voltage here is 18. This is 18 volt. Okay, and so V1 minus 18 divided by 6. Here it is, V1 minus 18 divided by 6. Second current is this voltage here minus this voltage. Okay, because we are calculating this current. This one is V1, which is 0. V1, which is 0. And this one is VO. Okay, so it is V1 minus VO divided by 4, which is this one here. We know that V1 is 0, so we just substitute by this one equals 0. Then you will have one unknown, which is VO. You need to calculate it. That's all. Okay, so this is the second example. Let's look at the third one here. This one, there's no difference between this one and the previous one. There's no difference. So let us try to erase this. Okay, so there's no difference between this one and this one. Let's see what's the difference. If you look at this one and this one, they are almost the same, just change numbers, 7 instead of 6 and 2 instead of 4. Okay, but the only difference here is this 7 ohm. This 7 ohm. But this 7 ohm will not have any effect. Why? Because we have this current equals 0, this current equals 0. Okay? And if this current equals 0, then the same current, the current in this resistor here, this current equals 0. This one is 0. If the current is 0, there's no voltage. There's no voltage across the 7 ohm. So if there's no voltage, this voltage, this one, and this one are the same. They are the same. Because there's no voltage. If you apply Ohm's law, V I R, the current equals 0. If the current is 0, then the voltage will be 0 times R, which is 7 here. So the voltage is 0. So again here V2 will be 0 volt, then V1 will be 0 volt. 0 volt. Okay, so when you apply nodal analysis at V1, then you will have three currents, this current here, and this current, which is this one here. This one will be this one. Okay, this one here. Okay, and the third one is 0. So we have this one, this current plus this current, which is again, it is the same current here, plus the third current, which is 0. And you know that V1 equals 0. Okay, so let's calculate the first current here. The first current is V1 minus 18 volt. Okay, V1 minus 18. So it will be V1 minus 18 over 7. Okay, plus second current is this voltage here, which is V1. V1 minus VO. This voltage is VO. So this one is V1. And this one is VO. V1 minus VO over the resistance, which is 2 ohm, equals 0. Because you know the third current is 0. That's it. You know that V1 is 0, then you have only one unknown, which is VO.